Oh, hello everyone. This is Hao Xu from University College London. Today I will give a talk about channel estimation in finite scattering environment. My talk will include the following 7 parts. In the first part, I will introduce the system model. We hope to estimate the channel state information of a system. So I will introduce two different schemes. The first one is the least square estimation. The second one is a low sample size sparse channel reconstruction. We call it L3 SCR scheme for short. In the first part, I will introduce the advantages and disadvantages of the proposed scheme. I will also introduce some other channel estimation schemes. Then I will introduce some simulation results and make a conclusion. This talk is based on this paper, Channel Estimation for Fast-Assisted Multi-User Millimeter Wave System, which has already been accepted by IEEE Communications Letters. As shown in the figure 1, we consider a millimeter wave uplink system, which consists of U users and one base station. Each user has a fluid antenna system with size W lambda and N parts. Here, W is the normalized size of the linear phase, and N parts are evenly distributed in this linear area. In contrast, the base station has M fixed antennas. If each user U transmits its signal XU at port NU, the signal received by the base station is given in this form. Here, G is the channel vector, and Z is the noise vector. We aim to estimate GU NU for any user U and any port NU. And we provide two schemes in the following. A very natural and direct way for channel estimation is the least square estimation scheme. In this scheme, all users' antennas switch synchronously over N ports and transmit orthogonal pilot sequences. At each port, a pilot sequence is transmitted T times. In the Tnth subframe, all antennas are located at the nth port. Then, in this subframe, the received pilot signal at the base station is given in this form. This term is received a pilot signal, and the second term is a noise. By right multiplying the normalized signal matrix, which is this one, by the pilot sequence QU, the least square estimation of the channel vector can be obtained as follows. Here, we see that G is a perfect channel vector, and the second term is the estimation error. Then the least square estimation of the channel matrix GU is given in this form. From the first formula, we see that the performance of the least square estimation scheme is mainly determined by T, which is a number of which is the times a pilot sequence is transmitted, and the second one is power, transmit power. However, since N is large, letting the antennas switch and measure the channel over all parts requires extremely high hardware switching and pilot overhead. So we hope to reduce the complexity for estimating the channel state information. And we propose the L3 SCR scheme. We noticed that millimeter wave channels have sparse scattering property. This indicates that if we know the sparse parameters of the channel from a user to the base station, for example, like the angles of arrival, angles of departure, and channel gains of different propagation paths, the channel from any part of this user to the base station can be constructed. So we estimate the sparse parameters by letting each fluid antenna transmit pilot sequences at K preset estimating locations instead of all N parts. Here, K is much smaller than N. By doing so, we can reduce the hardware switching and pilot overhead greatly. To this end, we first introduced the channel model. We let HU denote the channel matrix between the K estimating locations of user U and the base station. Note that here HU is different from the original complete channel matrix GU. GU the dimension of GU is M by N, but the dimension of HU is M by K. Based on the planar wave geometric channel model, HU can be expressed in this form. Here, LU is a number of propagation paths. Gamma UL is a complex channel gain of the L's path, and phi and theta are the angles of arrival and angle of departure of the L's path. The vectors AUR and AUT are steering vectors at the receiver and transmitter sides. They are expressed in this form. Here, D is equal to half wavelength. It is the adjacent spacing of the base antennas. Delta is the adjacent spacing of the estimating locations at the fluid antenna system. Here, H is expressed as the summation of several terms. We can also express it as in a matrix form. Denote matrices gamma U, AUR, and AUT. Then we can rewrite HU in the following matrix form. Letting all users' antennas switch synchronously over K estimating locations and transmit orthogonal pilot sequences T times at each estimating location. We can get the least square estimation of HU as follows. We do this by following similar steps in the previous section using the least square estimation scheme. In the following, we extract the sparse parameters of the channel from this least square estimation and then reconstruct the complete channel matrix GU. We estimate the sparse parameters in two steps. In the first step, we estimate the number of paths and angles of arrival. We estimate by jointly using the DFT-based method and angular rotation. Denote the normalized DFT matrix by omega, where each element is defined in this form. The DFT of the normalized least square estimation is then given by this form. Here, the product of omega Hermitian and AUR is a row sparse matrix with a 4-column rank. If M goes to infinity, only one element in each column is 1, while all the others are 0. Due to this property, the product of these 4 matrices is a row sparse matrix with LU non-zero rows, each corresponding to one of the AOAs phi. Here, LU is a number of propagation paths. Then we know that when M is large, this matrix H is an asymptotic row sparse matrix. Its power is concentrated on a few rows, while the remaining power is linked to the nearby rows. Here we say asymptotic for 2 reasons. First, M is a number of base station antennas, so it is impossible that M is infinity. M is finite. The second reason is that besides the product of these 4 matrices, we also have the noise term here. So we say that H here is an asymptotic row sparse matrix. To obtain an intuitive observation, we depict the power spectrum in figure 2. Under these settings, we denote the sum power of the mth row of this matrix by Fm, and we depict Fm over m for one channel realization in figure 2. From this figure, we see that there are 5 obvious peaks. This is because we set the number path L B5, and each peak corresponds to one of the 5 propagation paths. Therefore, from this matrix, we can obtain the estimation of the number of paths LU hat and the power peak indexes. However, the DFT-based estimation is coarse because its performance is limited by the resolution 1 over m. Therefore, we employ the angular rotation operation to further compensate the angular mismatch. We define the angular rotation matrix as follows: phi, matrix phi. Here, each parameter in this interval is a rotation parameter. By applying both the DFT matrix omega and the angular rotation matrix phi to the normalized least square estimation matrix, we obtain this formula. Due to the rotation matrix, the power peak at index m is rotated to m minus m phi. For a given ML hat, which is the power peak index obtained in the previous DFT-based estimation round, the problem is how to find the base phi L such that the estimated angle after compensation can best match the real one. We look for the best phi L by using the one-dimensional search method as follows. Once phi L is known, the estimation of the AOA phi UL can be obtained as follows. So far, we have known the number of paths LU hat and the AOAs phi for all users. Then we could calculate the matrix AUR hat. This is the first step for estimating the sparse parameters. Next, we go to the second step, where we estimate the angles of departure and the channel gains. We estimate by using the low complexity matched filters. Using this matrix obtained in the first step, we project the normalized least square estimation to the AOA steering matrix subspace as follows. Here, when m is large, the product of these two matrices can be approximated by the identity matrix. And each column of this matrix contains the AOD and channel gain information of one path. So we are now faced with a one sparse reconstruction problem. We needed to extract the channel gain information and AOD information from each column of this matrix. To this end, we define the following dictionary matrix D. Here, C is the size of the dictionary. We apply this matrix to the we apply D to this matrix and obtain this formula. The sixth element of this vector can be expressed in this form. And it is easy to see that the modulus of this element satisfy this inequality, which shows that the modulus of this element is no larger than the modulus of gamma UL. If C is large enough, we can always find an integer CL such that the difference of these two cosine terms is 0, and this inequality holds with equality. This indicates that if depicting the power of the elements of this vector over the indexes from 1 to C, we will see a peak. We will see a power peak at index CL. So we look for the power peak by one-dimensional search. Once CL is known, the LD theta and the channel gain gamma can be estimated as follows. So far we have successfully estimated the number of paths, the angles of arrival, the angles of departure, and the channel gains. With this information, we can reconstruct the whole channel based on the planar wave geometric model. So we can obtain the estimation of GU. This is the scheme, L3 SCR scheme we proposed for channel estimation for the fast assisted system. This scheme has some advantages and disadvantages. This scheme requires quite low computational complexity because in each step we use some simple algorithm, and this algorithm do not require high complexity computation like the channel inversions. And the second advantage of this scheme is that it can achieve high estimation accuracy when M is large. Of course, it also has some disadvantages. The first one is that in this scheme, the AOAs and LDs are estimated separately. Therefore, error propagation exists. This means that the estimation performance of the first step will affect that of the second step. So if the number of antennas at the base station is small, the estimation is inaccurate because if M is small, the estimation in the first step will be inaccurate. And this affects the performance of the second step. Yeah. So so far we have shown that in a sparse scattering environment, the CSI of a fast assisted system can be estimated using some standard tools. Besides the proposed L3 SCR scheme, we can also use some other schemes for the estimation, such as the orthogonal matching pursuit algorithm. This is also the scheme we compare in the simulation with our L3 SCR scheme. And there are some other schemes like the music method, e-spirit scheme, unitary e-spirit algorithm, and SAGE scheme. These methods differ mainly in terms of the estimation accuracy they achieve and the computational complexity levels they demand. Now I will show you some simulation results. We evaluate the estimation accuracy by considering three metrics. The first one is a sum rate of the system, which is expressed in this form. Here, tau is the loss from pilot signaling. And W is the linear receiver used by the base station to detect the signal of user U. The second metric is a normalized mean square error, NMSE, which is defined in this form. Here, GU hat can be any of these three matrices, depending on which kind of estimation scheme we use. The third metric is the average computational time required for carrying out the estimation scheme in one-channel realization. In these two figures, the effect of the number of estimating locations K and the number of base station antennas M is investigated, from which several observations can be made. Firstly, we see that when M is small, the OMP algorithm outperforms the proposed L3SCR scheme in terms of both NMSE and the sum rate. While when M is large, the situation reverses. This is because the proposed L3SCR scheme separately estimate the AOAs and AODs. The estimation error in the first step will therefore be passed to the second step. In contrast, the OMP algorithm jointly estimates the AOAs and AODs. Therefore, if M is small, the OMP algorithm can be applied to improve the estimation accuracy. Secondly, we see that when K increases, the NMSE of both the L3SCR and OMP schemes decreases monotonically, whereas the sum rate first increases and then decreases. This is because while increasing K can effectively improve the estimation accuracy, it also increases pilot overhead. Moreover, we can see that the NMSE of the least square scheme remains unchanged with both K and M. We will explain why in the next slide. Note that in many configurations, the LS method outperforms the other two schemes in terms of NMSE. However, it is important to recognize that the least square method requires very high pilot overhead. This results in a lower sum rate, as we can see from figure 4. This figure 5 depicts the NMSE and average computational time required for one-channel realization versus the SNR rho and the number of times a pilot sequence is transmitted, T. We can see that the log NMSE of the least square scheme decreases linearly with the SNR rho, while the log NMSE of the other two schemes reduce at the beginning and then saturate. The log NMSE of the least squares scheme can be expressed in this form. The first term is a constant. So we see that the log NMSE of the least square scheme is affected only by T and rho, and it decreases linearly with rho. This has already been verified by this figure 5. This formula also explains why it remains unchanged with K and M in the previous two figures. Differently, the performance of the other two schemes is affected not only by rho and also not only by rho and T, but also by K and M. From this figure, we can also see that the computational time of both L3SCR and OMP decreases with rho, and the OMP algorithm requires much higher computational complexity. This is because when rho is small, more iterations are needed for the algorithms to converge. And different from the L3SCR scheme, the OMP algorithm needs to compute matrix inversions, which is computationally intensive. So that's why the OMP scheme requires much more computation time than the L3SCR scheme. Now we make a conclusion for this talk. In this talk, we show that in a sparse scattering environment, the CSI of the fast-assisted system can be estimated and reconstructed using the geometric channel model and some standard channel estimation tools. We propose the L3SCR algorithm for channel estimation, which requires quite low computational complexity. We verify by simulations that in many configurations, the L3SCR algorithm can achieve high estimation accuracy. Due to the error propagation problem, in some configurations, the estimation of the L3SCR algorithm is inaccurate. In these cases, we show that some other standard tools, such as the OMP scheme, can be employed to improve the accuracy at the cost of computational complexity. So this is my talk about channel estimation for fluid antenna system. Thank you for listening. For more information about fluid antenna systems, please visit this website. Thank you.